Time is a river that never reverses. We are carried along its current, birth to death, sunrise to dusk, cause to effect, never sideways, always forward. And yet the laws of physics, the ones that govern particles, motion, and energy, don't care about direction. Their equations work the same in reverse. They describe a universe where the past and the future are mathematical mirrors. So why, in our experience, is time not a loop, but a slope? Why do we remember yesterday, but not tomorrow? Why does a cup shatter, but never reassemble? Why does a candle burn down, but never rise from its own smoke? The answer is entropy. Not a force, not a substance, but a tendency. A direction embedded not in particles, but in probabilities. Entropy is the measure of disorder, of options, of how spread out things can be. And the second law of thermodynamics tells us something profound. In any closed system, entropy never decreases. Disorder grows, order fades, heat spreads. The arrow of time points one way. But here's the twist. Entropy isn't just about decay, it's about becoming. Stars ignite because clouds of gas collapse in heat. Galaxies form from gravity's dance across billions of chaotic motions. Life itself, structured, self-replicating, complex, emerges not in spite of entropy, but because of it. Entropy is the reason your brain can hold a memory. It's the reason there was a past. The reason there will be a future. It is the silent clock of the cosmos, ticking not with gears but with imbalance. In this episode, we'll explore how entropy shapes the flow of time, how it powers creation, even as it foretells destruction, and how this quiet law governs not just the fate of stars, but the cracks in our coffee cups, the warmth in our breath, and the way we tell stories, with beginnings, middles, and ends. Because time is not just a measure, it is a direction, a consequence. A one-way unfolding written into the fabric of the universe. And entropy holds the pen. Entropy. A word whispered in physics textbooks and shouted in climate reports. A word so misunderstood that it's often used as a synonym for chaos or decay or doom. But entropy is not chaos, it is clarity. It's not the end of order, it's the reason order exists at all, if only briefly. The term comes from the Greek entrop, in transformation. It was coined in the 1860s by Rudolf Clausius, a German physicist searching for a way to describe something invisible, yet unavoidable. The gradual degradation of energy in any system. He needed a word for what was lost, not in substance, but in usefulness. A measure of how energy spreads, how it evens out, how it becomes inevitably less available to do anything interesting. That measure was entropy, and with it came a law. Not a law written in stone, but in heat. To understand why entropy matters, we must go back, not to stars or atoms, but to steam. In the 19th century, steam powered the world. Trains, ships, factories. The Industrial Revolution was built on the idea that you could heat water, make it boil, and turn expansion into motion. But a question haunted the great minds of the time. How efficient can a steam engine ever be? Why, even with the best design, does some energy always get lost? Why do engines get hot? Why do they leak work? A French engineer named Sodi Carnot began to ask these questions in the 1820s. He imagined an ideal engine, one that could extract the maximum possible work from a cycle of heating and cooling. No friction, no leaks. Perfect isolation. The engine was a thought experiment, a dream of perfection. And yet, even this ideal engine had limits. Carnot found that you could never convert all the heat into work. Not even close. Some of it must always go to waste, dispersed into the surroundings, never to be reclaimed. This wasn't a failure of engineering, it was a law of nature. Later, Rudolf Clausius formalized this observation. He wrote, "The energy of the universe is constant. The entropy of the universe tends to a maximum. Energy doesn't vanish, it transforms, it spreads, it becomes less concentrated, less useful. That is entropy." And this principle would become known as the Second Law of Thermodynamics. Where the first law told us that energy is conserved, the second law told us that energy has direction. It can move from hot to cold. It can power a machine, but it cannot stay organized forever. Even in a perfectly sealed system, No leaks, no noise. The energy inside will settle into a dull, useless soup. A state of balance. A state of maximum entropy. Entropy didn't come into physics as a thunderclap. It crept in, subtle, statistical, and quietly final. After Carnot and Clausius laid the foundations, the second law took its place not as a curiosity, but as a commandment. In any closed system, entropy never decreases. It always increases. Or, at best, stays the same. This isn't just a tendency, it's a rule of irreversible fate. You can compress gas into a canister, you can boil water into vapor, but you cannot unpop popcorn. You cannot unburn a match. You cannot unmix milk from coffee. Energy flows. It disperses. The second law ensures that once it spreads, it never reconcentrates. At least, not without help from outside. This is why machines wear down. Why stars exhaust their fuel. Why the universe isn't filled with tight, orderly bundles of energy but with sprawling clouds of it, gradually cooling. The second law doesn't just govern heat. It governs change. And it does something else, to something strange. It gives time a direction. Most equations in physics are time-symmetric. Run them forward or backward, and they still make sense. But the second law is different. It only runs one way. Entropy increases. Eggs crack, bodies age, and memories form. And we know deeply, intuitively, that these processes never go in reverse. This is the arrow of time, not drawn by clocks, but by conditions. It's not that time moves forward, it's that entropy does. By now, you've heard the phrase. Entropy is disorder. It's a useful metaphor, but a dangerously incomplete one. Entropy isn't messiness, it's possibility. Let's imagine a deck of cards. If the deck is sorted as to king, perfectly aligned, there's only one way it can look. But if it's shuffled, there are quintillions of possible arrangements, each one disordered. Each one more probable. Entropy is not just about how something looks, it's about how many ways it could be. Physicists call these options microstates. It's the hidden arrangements of particles beneath what we observe. What we call the state of a system, ice and water, gas in a room, is just a snapshot of many microstates. When entropy increases, it means the number of possible microstates increases. It's not destruction. It's diffusion. Think of an ice cube in warm water. At first it's distinct, structured. Its molecules are locked in a rigid lattice. But as it melts, the water becomes uniform. The molecules spread out. Energy evens. To the eye, the system looks less interesting. But to the universe, it's more likely. More options. More possible microstates, more entropy. And this is the heart of it. Entropy doesn't say what will happen. It says what tends to happen. It says that the most probable future is the one with the most ways of being. And once we started thinking this way, everything changed. Because someone came along to put that probability into math. In the late 1800s, a brilliant Austrian physicist named Ludwig Boltzmann asked a simple, devastating question. What if thermodynamics, this grand law of heat and energy, wasn't a mystical truth, but a matter of statistics? He imagined the world not as solids and fluids, but as trillions of atoms in constant chaotic motion. And he made a leap no one else had dared to take. Entropy, he proposed, is not about heat. It's about how many microscopic ways a system can be arranged, and still look the same from the outside. More ways equals more entropy. He even wrote it as an equation later, carved on his tombstone. S equals K log W, where S is entropy, K is Boltzmann's constant, W is the number of microstates, the number of hidden quantum arrangements that make up a visible state. Entropy wasn't disorder. It was math. It was probability. It was the logic of the likely. And suddenly, the second law wasn't just empirical. It was inevitable. The story doesn't stop with physics. No. In the 1940s, a young mathematician named Claude Shannon realized that entropy had a twin in an entirely different field. Information theory. When you send a message across a wire, through radio, or between neurons, you face a question. How unpredictable is the content? If you know what someone will say before they say it, there's no surprise, no new information. But if every word carries uncertainty, there's entropy. Shannon defined information entropy as a measure of surprise. The more possible messages, the higher the entropy. Suddenly, entropy was everywhere. In language, in communication, in biology, where DNA stores low-entropy blueprints inside high-entropy cells, in computers, where bits flip in ordered cascades to tame entropy into function. Entropy became the bridge between physics and knowledge, between heat and thought. By now, you may wonder, is entropy just a concept? Just a tool? No. Entropy is more than a number. It is a law of direction. It tells us not just what is possible, what is probable. It governs the tendency of systems to evolve toward more likely states. Not by force, but by math. It applies to everything. From steam in a cylinder, galaxies forming from cosmic gas, to the aging of your own body, entropy doesn't just describe change, it drives it. It whispers, gently but insistently, that everything flows outward. That heat will spread, that clarity will blur, that order will fade. But in that fading, something else begins. Time to us is more than a number. It's a pulse, a passage. A law written into the architecture of our lives. We feel it in the wilt of flowers, in the grain of hair, in the way laughter echoes into silence and never rewinds. When yet the strangest thing about time is not how fast it moves, but that it moves at all. Most of nature doesn't seem to mind which way time flows. A planet can orbit forward or backward, gravity doesn't care. Electrons jump, photons fly, forces push and pull, perfectly symmetrical in time. So where does the difference come from? Why is there such a profound split between the past and the future? The answer lies not in the ticking of clocks, but in the changing of conditions, in the asymmetry of entropy. Time, in physics, is a parameter, but in experience, it's a direction. And that direction emerges not from cause and effect, but from the increasing number of ways things can rearrange themselves. Entropy doesn't just move energy, it sculpts time. Imagine you drop a glass. It hits the floor and shatters into jagged shards. Now picture the reverse, the shards rising, reassembling, and landing gently on the table. You know it's fake. Why? Because every moment in the real version involves energy scattering, complexity increasing, information being lost into heat and sound and randomness. The reverse would require those pieces to coordinate perfectly, every molecule tracing back its path. It's not impossible under physics, but it's so improbable, so statistically rare, that it might never happen even once in the lifetime of the universe. This is what makes entropy different. It's not a force. It's a statistic, and statistics have direction. The probability of a broken glass becoming whole again is not zero, but it's infinitesimal compared to the forward scenario. And here lies the quiet brilliance. Most of physics is ambivalent about time, but entropy is not. Bouncing ball, a pendulum, a spinning planet, they obey reversible laws. But when entropy enters the scene, when friction warms, when air molecules mix, when patterns dissolve, time gains a fingerprint. That fingerprint is not visible in the laws themselves, but in the outcomes they prefer. And entropy always prefers the future. The laws of motion are symmetrical. If you recorded two celestial bodies dancing around each other and reversed the footage, you'd see no violation. The math would still hold. The gravitational pull, the acceleration, the velocities, they all obey time-neutral equations. But real life is not so forgiving. In your kitchen, soup cools. In a thunderstorm, warm air rises and becomes scattered rain. In your cells, chemical gradients flatten. These things don't reverse not because they can't, but because they overwhelmingly won't. And that distinction is everything. The second law of thermodynamics tells us that entropy increases. It is an absolute edict, but is an overwhelmingly likely outcome. The universe is not forbidden from rewinding. It just doesn't. And so, entropy becomes the only known law that gives time its signature. This asymmetry shapes reality in quiet but total ways. A newborn cries. Entropy increases. A star fuses hydrogen. entropy increases. You remember breakfast but not tomorrow's dinner. It's not because your neurons can't fire in reverse, it's because the storage of memory itself is a process that increases entropy by forming structure, by burning glucose, by pushing biological order outward into ambient disorder. We tend to think of time as a river, but entropy reveals its source. The past is a configuration with fewer possible microstates. The future is an ocean of probabilities, and that transition from fewer to more, from specific to general, is the slope of time. Memory is not a passive imprint. It's an act of entropy. To remember something, to record, store, retrieve information, your brain undergoes a cascade of molecular change. Neurons fire, chemicals shift, synapses adjust. And every one of those processes increases entropy. It's not because memory is messy, but because it is irreversible. To form a memory, your brain expends energy, gives off heat, and leaves the system more disordered than before. This is why you remember the past, but not the future. You might think, well, I can imagine the future, yes, but that's not memory. It's prediction, simulation, I guess. Memory is evidence, etched into biology, into molecules, into the very structure of matter. And that evidence only flows in one direction. This asymmetry is why it causes precede effects, why we see a rock thrown before we hear the splash, why the past feels settled and the future feels open. And this isn't just a human trait, it's universal. A hard drive, a tree ring, a fossil leech stores a record. But the act of recording always pays the entropy tax. But this raises an unsettling question. If entropy increases over time, why was the past so ordered to begin with? Why did the universe start low on the entropy scale? It's a puzzle that cuts deep because the early universe just after the Big Bang was incredibly hot and dense. And in thermodynamics, hot and dense usually means high entropy. But what made it low entropy was not temperature. It was structure war, rather, the lack of it. In those first microseconds, matter and energy were spread out almost perfectly evenly. No clumps, no galaxies, no black holes. And from a gravitational standpoint, that uniformity was incredibly ordered like a tightly wound spring. Over time, gravity amplified tiny fluctuations, forming stars, clusters, and voids. And with every step, entropy increased, so we find ourselves in a strange situation. The universe began with minimal structure, and out of that smoothness came the vast, evolving complexity we now observe. Galaxies swirl, stars ignite, brains think, all made possible because the cosmos started not in chaos, but in symmetry. It's beginning a low entropy. State gave entropy a runway. It gave time a slope. It gave stories a beginning. We say time flows. Entropy tells us it tilts. Imagine rolling a ball down a hill. The hill is steep, direction is obvious. You don't need a stopwatch to know which way is forward. Entropy provides that incline. It doesn't just govern heat, it governs sequence. The unfolding of events. The order of before and after. Without entropy, there would be no time as we know it. No cause and effect, no past to recall or future to imagine. Just a frozen block of possibility, symmetric, reversible, without change. Entropy fractures that symmetry. It gives the universe a gradient, a bias, a reason why the next moment isn't the same as the last. And that's what time is. It's not a tick on a clock, but a climb down the cosmic slope. So when you light a candle, hear a heartbeat, or watch a shadow stretch across the floor, remember this: what you are witnessing is entropy flowing, and with it, time. We often imagine entropy as the villain, the great unmaker, the ghost that haunts order, the final whisper in the collapse of all things. But this is only half the story. Entropy doesn't simply unravel, it enables. It's easy to see entropy as a destroyer. It is, after all, why castles crumble, why stars dim, why civilizations leave behind dust. But entropy is also a sculptor. It doesn't just erase structure. It provides the conditions that make structure possible in the first place. How? Because entropy demands flow. And flow of energy, of heat, of information, is the source of emergence. A world without entropy would be still, frozen, sterile. Everything would be in perfect balance, unmoving, inert. There would be no friction, but also no fire, no decay, but no breath. What entropy does is create the difference between one place and another, between hot and cold, high and low, concentrated and diffuse. And where there is difference, there is potential. It is precisely because the universe is uneven, because it is still becoming, that anything becomes at all. We do not live in a universe that is settled. We live in a universe that is still in motion. Sun burns because it is out of balance. It radiates energy because it must. Its core is a furnace of nuclear fusion. And the difference between that core and the cold of space creates the flow of light. Photons racing outward, carrying heat, driving winds, awakening chlorophyll. It takes just over 8 minutes for that light to reach Earth, and when it does, it collides with an entire planet out of equilibrium. Some of that light warms ocean currents. Some drives the weather, evaporating water that becomes storms. Some is caught by leaves used to split molecules of water and build sugars. Some becomes food. Some becomes thought. This imbalance, the energy gradient between our star and the void, is what powers everything. Entropy increases when energy flows, but that increase allows patterns to emerge along the way. Take a thunderstorm. Forms when warm air near the ground rises into cooler layers above. The resulting instability releases heat, forms clouds, sends down rain. From imbalance comes structure. Or consider plate tectonics. The Earth's crust breaks, slides, and rises not out of spite, but out of heat trapped inside a slowly cooling planet. From imbalance, continents form. Mountains rise. Minerals mix. Even the deep-sea vents, home to alien-like ecosystems, exist because of heat leaking from the Earth's core into a freezing ocean. Where heat meets cold, life begins. Everywhere you look, entropy's uneven march doesn't stifle change. It drives it. The cosmos is not boring because it runs down. It's interesting because it's not yet done running. In 1977, Belgian chemist Ilya Prigogine won the Nobel Prize for describing one of the most beautiful paradoxes in science. That in systems far from equilibrium, order can emerge spontaneously but only because entropy is increasing overall. He called these phenomena dissipative structures. The idea is deceptively simple and radically powerful. Some of the most striking patterns in nature arise not in spite of entropy, but because of it. Take the simple act of boiling water. Heat the bottom of a pot. Soon you'll see swirling cells of motion. Hexagonal convection rolls, endlessly forming and collapsing. These aren't random. They are structured responses to energy flow. Or look at a hurricane, fierce, vast, exquisitely organized. It's a spiral of warm air rising and spinning, formed entirely from a thermal imbalance between ocean and atmosphere. It doesn't defy entropy. It's enabled by it by taking disorganized heat from the sea and turning it into motion, wind, cloud, and rain. Hurricanes, convection cells, lightning, turbulence, these are entropy's artworks. They're brief, they're local, and they're not permanent, but they are real. Now take one more step. A living cell is a dissipative structure too. It gathers energy, expends it, stays alive for a while only, because it remains out of equilibrium. It does this by burning fuel, by breaking molecules, by releasing heat into its surroundings. And in doing so, it maintains its internal order for just a bit longer. Living things in this view are entropy surfers riding the crest of cosmic imbalance. Borrowing time from thermodynamics, spending it on metabolism, movement, memory, they are not exceptions to the second law. They are its most elegant consequence. Life feels like resistance. It grows upward when gravity pulls down. It builds structure where randomness waits. It memorizes, metabolizes, replicates. To the untrained eye, life seems like entropy's opposite. But to the universe, it is something far more interesting. Life is entropy's accomplice. A living cell is not a closed system. It is porous, responsive, inhale, exhale, input, output. It takes an ordered energy, sunlight, sugars, oxygen, and uses it to maintain itself, to grow, to adapt. And in doing so, it releases heat, waste, and disorder into its surroundings. Every act of life, every thought, every heartbeat, every breath is thermodynamically expensive. It buys a moment of order. at the cost of greater entropy somewhere else. This is not failure. This is how life works. What sets living things apart is not that they reduce entropy, but that they channel it locally, decreasing disorder while globally obeying the law. Life is not the antithesis of the second law. It is one of its most dazzling expressions. And life doesn't just respond to entropy, it learns to exploit it. Bacteria position themselves along thermal gradients. Plants orient their leaves toward the sun's most efficient angle. Animals consume energy-rich molecules to do the improbable: heal, hunt, remember, run. Even evolution, the slow sculpting of traits over eons, can be seen as a kind of entropic search. A billion random changes, most discarded, a few retained. Patterns emerge, forms stabilize, and adaptations bloom. None of this violates entropy. It all flows from it. Entropy is not the end of life. It is its background rhythm, the drumbeat beneath biology's fragile choreography. And the more we study living systems, the more we see this elegant trade. Order within, paid for by disorder without. To live is to be out of balance, and to stay alive is to manage that imbalance just a little longer. Now lift your eyes beyond the cellular, beyond the organic. Look up at the stars, each one a beacon of imbalance, a nuclear engine fighting collapse, a monument to thermodynamic difference. Stars are not quiet, they rage. But in that raging, they give the cosmos its canvas. From the birth of stars come solar systems. From their deaths, the heavy elements, carbon, oxygen, iron, are scattered into space. Everything you are was once forged in that violent entropy. But it doesn't stop with elements. From the chaos of stellar birth clouds emerge planetary orbits. From planetary surfaces emerge climates. From climates, oceans, atmospheres, weather, and eventually, if conditions permit, consciousness. Not because entropy paused, but because it flowed. From starlight to sugar to synapse, entropy moves, and as it moves, it creates spaces where thought can form. Minds, too, are entropic. They metabolize fuel, they burn glucose, they generate heat. To think is to spend energy, to sort, to store, to reflect. And just like memory, thought is directional. Your ideas travel from known to unknown. From order to possibility. Brains do not escape entropy. They ride its wave, moment by moment. And they do something truly astonishing. They model entropy. They imagine time. They forecast futures. A brain is not merely reacting, it is predicting. It is trying to find patterns in the noise. From cells to civilizations. From hydrogen atoms to humans asking what entropy means, the very act of questioning this law is made possible by the temporary, structured complexity that this law has allowed. So when we say entropy always wins, yes, it does. But what a game it plays along the way. Stars are temporary. Life is temporary. Even thought is a flicker, but none of it is waste, because each pattern, each process, each pulse of order that briefly slows the flood is a masterpiece made possible by the river's flow. Entropy is not a flat field. It is a tilted stage. And from that slope rise galaxies, hurricanes, and minds that wonder why. The universe is a story told across eons, and entropy is its narrator, soft-spoken, patient, unrelenting. We often speak of endings in terms of drama, fiery destruction, violent collapse, cataclysm, but entropy imagines a different finale, not a bang, but a fade. In the beginning, the cosmos was ablaze with imbalance, hotter than stars, denser than black holes, raw potential everywhere. But over time, like steam escaping from a cooling kettle, that intensity has dissipated, flowing outward into structure, then into silence. We do not live in a universe at rest. We live in one still spilling its original heat, still tumbling toward thermodynamic equilibrium, a place where all gradients flatten, where nothing moves because nothing must. This is not peace. It is the absence of possibility. In the long view stretching beyond stars, beyond galaxies, entropy isn't just something that happens inside the universe. It shapes the very future of the universe. The day will come when there are no engines left to run. There's no warmth left to disperse, no boundary between hot and cold. That's what entropy wants. Not destruction, not chaos, just stillness. And the cosmos, for all its brilliance, is slowly preparing to oblige. We measure our nights by starlight, but the stars are not forever. Each one is a furnace, balancing on a razor's edge, gravity pulling inward, fusion pushing outward. It's a delicate agreement, but it's not eternal. Now, stars, like everything else, burn through their fuel. They are finite machines in an infinite sky. Some will end quietly. Like our own sun, shedding their outer layers in graceful planetary nebulae, leaving behind white dwarfs no bigger than Earth, but unimaginably dense. These dwarfs will shine for trillions of years, then go dark, cold, crystallized, forgotten. Others will end in fury. Massive stars collapsing in on themselves, detonating as supernova, seeding the galaxy with gold, iron, and oxygen. From these explosions, remnants remain. Neutron stars with the mass of suns crushed into the size of cities, or black holes so collapsed, so curved, that nothing, not even light, can escape. Each death writes a new chapter in Entropy's journal, not because stars prefer to end, but because they are caught in the rules of thermodynamics. Every joule of light they give, every neutrino they release, is a debt to disorder. They shine, yes, but only by breaking down. And as the centuries pass, the starfield's thin, the luminous age dims. Entropy does not extinguish stars. It lets them burn, then waits. If entropy is a tide that rises everywhere, then black holes are its greatest floodplains. They're not merely collapsed stars. They are boundaries in space-time, horizons beyond which information falls and does not return. Black holes, as strange as they are, seemed for decades to violate thermodynamics. They had mass, they had spin, but they had no temperature. How could they grow in entropy if they didn't even radiate? And then Hawking changed everything. In 1974, Stephen Hawking combined general relativity with quantum field theory, and he discovered something almost unthinkable. Black holes aren't perfectly black. They radiate. Not much, not quickly, but enough. This radiation, now known as Hawking radiation, means that black holes have a temperature, and if they have a temperature, they have entropy. In fact, a black hole's entropy is enormous. The entropy of a black hole exceeds that of any known object of similar mass, and yet it's measured not by what's inside, but by the surface of the event horizon. This shocked physicists. It suggested that the information content of a volume might live on a boundary, that space-time itself might be holographic, a projection from a surface into a space. Here, entropy becomes not just a measure of disorder, but a clue to something deeper, that the universe may be more informational than physical, that entropy isn't just counting heat, but meaning. But there's a deeper mystery. What happens to the information that falls into a black hole? Does it vanish? Does it stay encoded on the horizon? Does it escape in the slow whisper of Hawking radiation? This is the black hole information paradox, and it cuts to the core of physics. Because if entropy measures hidden information, and if black holes erase it, then perhaps entropy itself is incomplete. Or worse, our understanding of reality is. Some theories say information escapes subtly, encoded in radiation. Others say it's scrambled but preserved. Still others propose firewalls, violent boundaries that vaporize incoming matter. We do not yet know. But what we do know is this. Black holes are not the end of entropy. They are its monuments. Silent, hungry, almost eternal. And yet not quite. Because even black holes, entropy's darkest vessels, will one day fade. The future isn't fire, it's equilibrium. We imagine endings with explosions, with grand finales, with a bang. But entropy doesn't deal in spectacle. It deals in settling. The end of time, if it comes, will be cold. Not because something failed, but because everything finished. This is the idea of heat death, a state where all usable energy has been spread too thin to do anything at all. A state where every gradient has been erased, every light extinguished, every motion ceased. At that point, the universe will not be dead. It will be indifferent. Because even atoms need contrast to collide. Even information needs difference to be stored. Even thought needs warmth to flicker. In the era of heat death, the cosmos will remain vast and silent, filled with low-energy radiation, stretched thin by expansion, trapped in uniformity so complete that nothing can ever change again. No new stars, no new entropy, because there is nothing left to be lost. This is not destruction. It is the final equilibrium of everything that ever was. Though it sounds desolate, it is not cruel. Entropy has no intention, no judgment, no malice. It is simply the tendency of the possible. It's fulfilled completely. Still, before the final hush, there will be whispers. Long after the last star collapses, after galaxies have dissolved into dust and the cold has crept into every corner of space-time, a few monuments of gravity will remain. The black holes. These are not eternal. Thanks to the quantum dance of uncertainty, black holes slowly leak energy into the void, an effect known as Hawking radiation. This radiation is faint, almost imperceptible in the short scale of cosmic time. But in the eons ahead, it becomes the last performance in the universe. As a black hole loses mass, it gets smaller, and as it gets smaller, it gets hotter, and as it gets hotter, it radiates faster. This forms a slow crescendo. Billions of years of quiet, followed by a sudden final burst. A black hole's last breath. No light escapes, no sound accompanies it, just a fade, a silence, and then nothing. And so, the very entities once thought to devour the universe become the final source of its light. When the last black hole evaporates, the universe will not be empty. It will be featureless. All the structure that once danced between stars, planets, and people, dispersed into randomness too perfect to be noticed. The universe, once so full of purpose, will carry only presence, a canvas wiped clean. When there are no more processes, when there is no more information to lose, when no event distinguishes itself from any other entropy, will have reached its final destination. But that destination isn't oblivion, it's completion. Entropy is not the villain of physics. It's not the destroyer, it's the keeper of closure. Because the universe didn't begin in silence. It began in a roar of difference, hot and dense and filled with tension. It had to settle. And entropy was the law that wrote its arc from beginning to balance. We often ask what the point of it all was. Why stars were born, why life emerged, why we remember anything at all. But that question assumes there was a reason. Entropy offers a different kind of answer. Not a reason, but a path. Everything that ever happened was one step further down that slope. Not by accident, but by inevitability. And somehow, in that long decline, order formed. Patterns appeared, eyes opened. For a brief window of time, the universe became capable of knowing itself. And even if memory fades, even if structure dissolves, even if time itself becomes irrelevant, for a while it mattered, because meaning doesn't require permanence. It only requires emergence. So when we speak of the end of, the death of stars, and the flattening of all difference, we're not speaking of failure. We're speaking of fulfillment. Of a law that was never broken. Of a journey that was never paused. Entropy always wins. But in its wake, it gave us galaxies, music, minds, and love. Fleeting, yes, but exquisite. We do not fight entropy. We ride it. And in doing so, we leave behind the most unlikely of things. A trace. You are not sealed like a machine. You are not closed like a perfect box. You are porous, open to the flow of light, air, water, and time. From your first gasp of breath to your last quiet exhale, you exist in constant exchange. With every heartbeat, every bite of food, every second of thought, your body participates in a grand thermodynamic cycle. You are alive because you do not conserve energy. You transform it. You take in low entropy substances, oxygen, carbohydrates, amino acids, rich in chemical potential and structure. And you release high entropy products, heat, carbon dioxide, water, scattered, broken down, simplified. This transformation is not wasteful. It is how life sustains itself. You are not a thing. You are a process, not static, but dynamic. Not preserved, but perpetually renewed through flow. And that flow has a cost. Every second you live, you pay the toll of entropy. You buy the next second by spending a little more order. You remain a pocket of improbability, temporary island of structure adrift in an ocean of increasing disorder. And you endure, not because you resist entropy, but because you ride it for a while. You breathe without thinking, but every breath is a transaction, a precise thermodynamic negotiation with the atmosphere. When you inhale, you're not just filling your lungs, you're inviting oxygen atoms born in the cores of ancient stars into your blood. These oxygen molecules are seekers. They move swiftly, purposefully, guided by gradients in pressure and diffusion. Once inside your cells, they participate in a ritual older than language. Inside your mitochondria, tiny organelles descended from ancient symbiotic bacteria, they help dismantle molecules of glucose. This is respiration. It's not the rising and falling of your chest, but the intimate chemistry of life, electron by electron. Through this slow, controlled unraveling of fuel, your body captures usable energy in the form of ATP. Molecular currency spent on motion, repair, awareness. But there is no free energy. With every molecule of ATP created, disorder is increased elsewhere. The products of respiration, carbon dioxide, heat, entropy, are expelled into the world around you. You breathe in opportunity. You breathe out entropy. It's a quiet process, invisible, but it shapes every action you take. It's from the lift of your eyelids, to the shape of a sentence, to the beat of your heart. You are not only made of star stuff, you're fueled by it, and its transformation carries a cost. You were not born in balance. As a baby, your body was full of gradients, chemical, electrical, thermal. Your cells were tightly organized, your enzymes precise, your DNA freshly copied. You were a miracle of coordination, billions of tiny engines running in perfect choreography. But even miracles have thermodynamic consequences. Every act of growth, each cell division, each new synapse, each heartbeat left behind residue. Tiny inefficiencies, molecular errors, imbalances. Entropy didn't rush in, it whispered, subtle and patient, nudging the system away from its improbable symmetry. And so you aged. Not because anything broke, but because everything worked as long as it could. Proteins began to misfold. DNA acquired mutations. Cellular cleanup mechanisms faltered. Mitochondria, the power plants of your cells, became less efficient, leaking energy and reactive molecules into their surroundings. These weren't malfunctions. They were thermodynamic inevitabilities. Your joints ache not because you move too much, but because motion is paid for in wear. Your skin wrinkles not because it forgets elasticity, but because structure requires constant renewal and renewal slows. Aging is not a failure of biology. It is the success of entropy over time. You are not winding down because you broke. You are winding down because you ran brilliantly for longer than the odds should have allowed. In that sense, aging is not the opposite of youth. It is its receipt. A quiet record of energy spent wisely. Entropy does not hate life. It allows it, and eventually it reclaims it. Not cruelly, not quickly, but as part of the balance written into everything that moves. You can close your eyes and remember, not just facts, but feeling. The sound of your childhood door creaking, the scent of rain on concrete, the face of someone long gone. This ability is extraordinary, but it is also entropic. Memory is not a playback. It's a reconstruction stored imperfectly in the fragile wiring of your brain. Each memory is a chemical trace, etched through molecular work. Proteins folded, signals amplified, circuits rearranged. To remember something, anything, you must change. You must consume energy. You must allow a little more disorder into the world around you. This is not metaphor. It is thermodynamic fact. Your hippocampus, the seat of memory, is a constant engine of entropy. When you form a memory, it raises the entropy of your surroundings by releasing heat, using oxygen, triggering synaptic adjustments. You never remember for free. And this is why you don't remember the future. There is no trace to reconstruct. No entropy trail to follow. The future is smooth and undisturbed. The past is rippled with friction. That asymmetry between what has left a mark and what is not is what gives time its arrow. And you follow that arrow not just with your body, but with your mind. Entropy touches your thoughts, but it also shapes your heart. There's a reason the most beautiful moments feel like they're slipping away even as they unfold. There's a reason joy is tinged with sadness and love with loss. Emotion is the echo of time. You grieve because something is gone and because it mattered. You celebrate because something was brief and because it happened. Feelings are not separate from physics. They arise because of it. Entropy ensures that nothing lasts unchanged. And so, the most meaningful moments are the ones we know will fade. A newborn's first breath is the final hug with someone you'll never see again. Conversation you didn't know would be the last. These moments carry weight because they are finite. Entropy makes them rare, and rarity creates reverence. In a timeless universe, love would mean nothing. Without decay, beauty would lose its urgency. Without endings, beginnings would be unremarkable. We do not feel in spite of physics. We feel because of it. Entropy does not steal meaning. It distills it. It creates a world in which the fleeting is sacred. And the fact that things end is precisely what makes them worth remembering. Imagine a universe with no entropy. Nothing changes. No heat flows. No stars ignite. No stories unfold. A place without before or after. A place without difference. Would anything matter? Meaning is not born from stillness. It emerges from change, from difference, from transformation, from the asymmetry between now and then. Entropy gives us that asymmetry. It gives us time. Time gives us story. You are not merely alive. You are happening. You are the unfolding of choices, consequences, emotions, and entropy woven into a moment that will never come again. If entropy did not increase, there would be no reason to do anything. No reason to care. No reason to love, to try, to weep, to learn. Meaning is temporal, depends on the past being different from the present and the future being uncertain. Entropy ensures that the future is never fully known, and in that uncertainty lies possibility. It is not chaos, it is opportunity, paid for by time, experienced as change, understood as meaning. So the next time you light a candle, or watch a leaf fall, or hold someone's hand, remember this. You are participating in the very law that governs the stars. And in that moment, however small, you are turning entropy into something more. You are turning it into life. We often think of laws as limits, boundaries that say, you cannot go further. But some laws, like entropy, don't limit. They reveal. They show us what's possible and what must change. Entropy is not a villain. It is not a shadow waiting to consume the light. It is the reason the light can shine at all. Without entropy, there would be no flame, no sunrise, no heartbeat, no ticking clock, because nothing would flow, nothing would age, nothing would become. We live in a universe built on transformation. Everything that is, once wasn't, and everything that is, will someday no longer be. Entropy is the quiet witness to this motion. It does not speak, it records. It does not rush, but it remembers. When you touch a stone warmed by the sun, when you light a match or share a meal or exhale a breath, you are moving energy from order into openness, from potential into memory. It's easy to think of entropy as loss, but what it really brings is story. Because without change, without imbalance, there would be no narrative at all. No surprise, no arc, no meaning. The universe would be a single frozen moment, infinitely still, infinitely dull. But that is not the universe we live in. We live in the heat of tension, in the afterglow of expansion, in the ebb and flow of probability. Entropy has created stars that live for billions of years and insects that live for only hours. It has carved rivers, powered empires, broken down mountains, and woven the neural nets in your mind. It is not kind, it is not cruel, it simply is. And in its ceaseless unfolding, it has made room for complexity, for life, for language, for love. We think of beauty as the opposite of entropy, but perhaps it is the product of it. A temporary balance between chaos and clarity. You are not apart from this process. You are its expression. You are what entropy looks like when it builds itself into thought. You are a structure that briefly remembers its own impermanence. You're an arrangement of energy just improbable enough to notice that everything changes, and that this matters. Entropy will one day dissolve every form, cool every sun, flatten every difference. But it will have done so after creating stars and forests, minds and music, questions and kisses and ancient stones that remember human hands. It will have allowed a universe to tell its story in 1,000 million ways. Each of them brief, each of them miraculous. This is the beauty in the breakdown, not that things fall apart, but that they come together first. That they burn brightly just long enough to leave behind warmth, wonder. We live in a universe that is dying, but we also live in a universe that, for a while, knows it. And in that knowing, we are not diminished. We are made more. Because if everything fades, then everything counts. If every structure is borrowed, then every breath is sacred. Entropy teaches us that there are no permanent things. It's only moments, only motion. And perhaps that is enough. Perhaps more than enough. So the next time something ends, a song, a season, a love, a life, remember, you are not watching a tragedy. You are witnessing the final grace of a system that once beat against the odds, that once existed despite the math. Entropy always wins, but before it does, it creates everything that matters. And we, for a while, get to be the part that watches. This is Cosmic Canvas, where science becomes story, and every law is painted in meaning, till the next unfolding. Keep wondering forward.